Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is DC power. Our objective is to take a close look at the different permutations of power calculations for DC electricity, sometimes collectively known as Watt's laws. Additionally, we'll review power and energy and efficiency calculations and introduce a device used to measure power known as the wattmeter. Power is a pivotal concept for this lecture series and serves to unify a number of previously independent topics. As such, expect numerous shoutouts to previously covered material. If at any time you are presented with material you have never seen or only dimly recall, please take the time to visit these lectures and come up to speed. Recall during the Energy and Power lecture, available at the Big Bad Tech channel, our first shoutout, I introduced the general concept of power, where power is the time rate use or production of energy, where 1 watt is equivalent to 1 joule per second. Energy can take many forms, but is most easily conceptualized as expressing a force for a certain distance, where energy is force times distance. If I move an object that resists me with 5 newtons of force, a distance of 4 meters, I have put 5 newtons times 4 meters, or 20 joules of energy into this system, where 1 joule is the SI unit of energy, equivalent to 1 newton of force expressed at a distance of 1 meter. Energy is the capacity to do work, and I like to think of energy as a quantity of fuel. By way of an analogy, one can think of every single joule of energy as a piece of firewood. In this case, 20 pieces of firewood got loaded into this system. How rapidly one gets this energy into or out of a system is power. Power is the time rate expenditure or production of energy. Power is energy per unit time. In keeping with this firewood analogy, think of the chores you did as a kid. Those of you that live in the colder regions are no doubt intimately familiar with the never-ending chore of cutting, splitting, stacking, and hauling firewood. While essential for survival, this task is not always approached with vigor and potency. Quite often, there is an associated amount of bitching and feet dragging accompanying this task. If on a cold, dark winter night you've ever had a coat thrown in your face and been told to bring in 20 pieces of firewood or freeze to death, you got one of two options. One, you can mope and whine and just pick at it over a long span of time, carrying maybe 2 or 3 logs every trip back from the woodshed. Or 2, just go load a sled with 20 pieces of firewood and drag it back to the house as quickly as possible. The point being, energy is a quantity, whereas power is the rate of change of that quantity. Power is the rate of change of energy over time. In this analogy, energy is like a quantity of firewood, which is a quantity of fuel, and power is how fast that pile of firewood or fuel is built. Again, power is a time rate production or consumption of energy. Let's say we've got two 20 joule tasks, where one is accomplished powerfully over a span of 1 second, and a similar 20 joule task is accomplished less powerfully over the span of 10 seconds. Power is energy over time. The first task power input is 20 joules over 1 second, or 20 joules per second, or 20 watts, where again 1 watt is equal to 1 joule per second. The second task power input in contrast is 20 joules over 10 seconds, or 2 joules per second, or 2 watts. Although both tasks ultimately necessitated the same expenditure of 20 joules of energy, the first task was accomplished in less time with a more powerful 20 watt input, whereas the second task was accomplished in more time with a less powerful 2 watt input. It makes sense. Moving on, let's now tie power and energy with our understanding of voltage and current. Recall during the Basic Electrical Quantities lecture, available at the Big Bad Tech channel, I introduced electrical power, where electrical power is the product of voltage and current. Power equals voltage times current, or in terms of units, 1 volt times 1 amp equals 1 watt. Expressed in shorthand, P equals V times I. Additionally, recall that both the volt and the ampere are derived units, where 1 volt is 1 joule of energy per coulomb of electrons, and 1 amp is 1 coulomb of electrons moving by a point in 1 second. A coulomb, by the way, is a group of electrons, kind of like a dozen eggs, only it is a lot more than a dozen. Using the units to aid us, we realize that our power equation of voltage times current is 1 volt times 1 amp, which simplifies to 1 joule per coulomb times 1 coulomb per second. Coulombs cancel out to yield joules per second, or watts. Think of the properties voltage and current independently, and how each of these two properties influence power. Voltage is a measure of how much energy a group of charges possess. 1 volt is 1 joule of energy per coulomb of charges. Returning to our firewood analogy, this is like how many pieces of firewood you fit in your arms on the way back from the woodshed. If you carry a lot of firewood in one trip, that's a lot of energy or a lot of voltage. If, however, you carry just a handful of sticks, that's not a lot of energy, equivalent to low voltage. Current, in contrast, is a flow rate measurement of how many charges pass by in a given time. 1 amp is 1 coulomb of charges per second. Returning to our firewood analogy, this is like the rate of speed you travel from house to woodshed and back. If you run back and forth real quick, that's a lot of flow or a lot of current. If, however, you just dawdle along and drag your feet, that's not a lot of flow, equivalent to low current. Now think about these properties together. What does the product of voltage and current mean? Consider an occasion characterized by low voltage and low current. Each packet of charges carries only a small amount of energy, and a packet of charges arrives only occasionally. Energy does accumulate, however the rate of change of energy or power is low. This would be equivalent to slowly walking back and forth between the house and the woodshed carrying a stick or two at a time. It's going to take a long time to get the job done because it's not being done powerfully. Conversely, consider an occasion characterized by high voltage and high current. Each packet of charges carries a large amount of energy, and packet after packet of charges arrives in rapid-fire succession. Energy accumulates, and it does so at a tremendously fast rate. This is an occasion of high power. This would be equivalent to sprinting back and forth between the house and the woodshed dragging an ox cart of logs at a time. The job is going to get done real quick because it's being done powerfully. Now that we've got a general understanding of the concept of power, let's discuss the mechanics behind calculating electrical power. Again, electrical power is voltage times current. P equals VI. Consider a 12-volt source and a light bulb modeled as a 60 ohm resistor. An application of Ohm's law demonstrates the light bulb will draw 200 milliamperes of current. We can analyze this system's power from two different perspectives, the source and the load, with the understanding that power input always equals power output. Active elements like voltage sources supply power, whereas passive elements like resistors dissipate or consume power. Power in always equals power out. This does not mean all power gets directed towards useful output, but rather that all power supplied is eventually directed somewhere, useful or otherwise. The source induces a 12-volt rise and supplies 200 milliamperes of current, whereas the load experiences a 12-volt drop and 200 milliamperes of current. Power is voltage times current. 12 volts times 200 milliamperes demonstrates the source is providing 2.4 watts of power, and the load likewise consumes 2.4 watts of power. Power in does indeed equal power out. For such simple circuits, this comparison of input and output power may seem unnecessary. However, for later, more complicated circuits, this makes a great way of checking your work. If at any time the summation of input power does not equal the summation of output power, you've made a mistake and need to re-inspect your numbers. Note that in order to arrive at these power figures, it first necessitated us performing an Ohm's law calculation to determine current. While this is always an option, it is not the most efficient means of performing power calculations, and more expedient methods exist. As you're no doubt aware, the various permutations of Ohm's law demonstrates that current equals voltage divided by resistance, voltage equals current times resistance, resistance equals voltage divided by current. Additionally, you are aware that power equals voltage times current. We can use these permutations of Ohm's law to derive other methods of calculating power. For example, given power is equal to voltage times current, and current is equal to voltage divided by resistance, we can substitute V over R for I in the power equation. This demonstrates that power is equal to voltage times voltage divided by resistance, or voltage squared over resistance. In the above example, 12 volts squared divided by 60 ohms similarly demonstrates that the load consumes 2.4 watts of power. Additionally, given power is equal to voltage times current, and voltage is equal to current times resistance, we can substitute IR for V in the power equation. This demonstrates that power is equal to current times resistance times current, or current squared times resistance. In the above example, 200 milliamperes squared times 60 ohms similarly demonstrates that the load consumes 2.4 watts of power. Let's add these permutations to the power equation to our growing arsenal of tools. Ohm's law demonstrates that voltage equals current times resistance. Current equals voltage divided by resistance, and resistance equals voltage divided by current. The power equation unified with Ohm's law demonstrates that power is equal to voltage times current, power is also equal to voltage squared divided by resistance, and finally power is also equal to current squared times resistance. You note beyond the means of simplifying power calculations, the two additional derivations of the power equation also simplify the practical measurement of power. Using the first equation, where power equals voltage times current, necessitates a technician measure both voltage and current, implying two time-consuming measurements need to be made. First, a technician would have to measure the voltage drop across the load using a voltmeter. Then they'd have to power off the system, break the circuit, insert an ammeter, turn the system back on, get a current reading, and then multiply these readings together to get a power figure. Given these additional permutations, far more efficient means exists. For example, using the second permutation, where power equals voltage squared divided by resistance, simply necessitates a technician measure voltage across a known resistance. Similarly, using the third permutation, where power equals current squared times resistance, simply necessitates a technician measure current through a known resistance. These permutations imply that shortcuts exist that can save you serious time in lab. Additionally, given there exist numerous methods to calculate power, there are ample opportunities to check your work. All methods should yield the same answers. If they don't, you are doing it wrong. Try this set of example problems on for size to see if you're tracking. Given these known values, see if you can solve for power experienced by the system using the most efficient and direct manner possible. Express all answers in proper engineering format to the tens place. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Our first problem features a 270 ohm resistor experiencing a 48 volt drop across it. We're being asked to solve for power. Power is voltage squared over resistance. 48 volts squared over 270 ohms yields 8.5 watts of power. We can use Ohm's law and a different permutation of the power equation as a means of checking our work. Ohm's law demonstrates that current is voltage over resistance. 48 volts over 270 ohms yields 177.8 milliamperes of current. Power is equal to voltage times current. Substituting in our given values similarly demonstrates this resistor is experiencing 8.5 watts of power. Our next problem features a resistor with a color code of green, blue, brown, experiencing 26 milliamperes of current through it. We're being asked to solve for power. A color code of green, blue, brown means 5, 6 with 1 0 after it, or 560 ohms. Power is equal to current squared times resistance. 26 milliamperes squared times 560 ohms yields 378.6 milliwatts of power. We can use Ohm's law and a different permutation of the power equation as a means of checking our work. Ohm's law demonstrates that voltage is equal to current times resistance. 26 milliamperes times 560 ohms yields 14.6 volts. Power is equal to voltage times current. Substituting in our given values similarly demonstrates this resistor is dissipating 378.6 milliwatts of power. Finally, our last problem features an unknown resistor experiencing a 9.9 volt drop across it and 45 milliamperes of current through it. We're being asked to solve for power. Power is equal to voltage times current. Substituting in our given values demonstrates this resistor is dissipating 445.5 milliwatts of power. We can use Ohm's law and a different permutation of the power equation as a means of checking our work. Ohm's law demonstrates the resistance is voltage over current. 9.9 volts over 45 milliamperes yields 220 ohms of resistance. Let's use both permutations of the power equation to double and triple check our work. Power is equal to voltage squared divided by resistance. Substituting our given values similarly demonstrates that the load is dissipating 445.5 milliwatts of power. Power is equal to current squared times resistance. Substituting in our given values similarly demonstrates that the load is dissipating 445.5 milliwatts of power. Given these calculations yield the same result, I've got a reasonable degree of confidence our results are correct. As we did in the Ohm's law lecture, let's plot current and power as a function of voltage for fixed resistance. Consider a 240 ohm resistor that experiences 0 to 24 volts in 2 volt increments. With a 0 volt differential across it, no current flows through it and it dissipates no power. If we step voltage up to 2 volts, an application of Ohm's law demonstrates that we should expect 8.3 milliamperes of current and the resistor to dissipate 16.7 milliwatts of power. If we step voltage up to 4 volts, an application of Ohm's law demonstrates we should expect 16.7 milliamperes of current and the resistor to dissipate 66.7 milliwatts of power. If we perform the same calculations in 2 volt increments, we should observe every increase in voltage to result in proportional increase in current. Notice how the current at 4 volts is twice that observed at 2 volts. If we step voltage up to 8 volts, the current at 8 volts is twice that observed at 4 volts. If we step voltage up again to 24 volts, the current at 24 volts is 3 times that observed at 8 volts. In short, Ohm's law is a linear property. and when current as a function of voltage is plotted, the results speak for itself. Every increase in voltage results in a proportionate increase in current. Power, in contrast, is not a linear property, but rather geometric in nature. Power at 4 volts is 4 times that observed at 2 volts. We step voltage up to 8 volts. Power at 8 volts is 16 times that observed at 2 volts. If we step voltage up to 24 volts, power at 24 volts is a full 144 times that observed at 2 volts. In short, power takes off like a rocket ship because it is a nonlinear geometric property. It is for this reason accurate voltage and current measurements are so important. Any increase in voltage results in a proportionate increase in current and a geometric increase in power. Lacking accurate measurements, it would be all too easy to reduce an otherwise functional component into a useless smoking husk. Moving on, I present you with your existing arsenal of tools, 3 versions of Ohm's law and 3 permutations of the power equation, 6 arrows with 6 sharp tips. Can you use these 6 arrows to make 6 more sufficiently deadly arrows for your quiver? If you are as mathematically competent as I expect you to be, you should be capable of algebraically manipulating these equations to solve for unknown quantities. For example, given known voltage and known power, we should be able to algebraically manipulate this entry to solve for resistance. Start by performing the inverse operation of both sides to get resistance on top. Multiply both sides by voltage squared. Voltage squared cancels out on one side, where we're left with resistance equals voltage squared over power. This is yet another arrow in our quiver. This equation implies that given known voltage and known power, we can solve for unknown resistance. Similarly, given known power and known resistance, we should be able to algebraically manipulate this same entry to solve for voltage. Multiply both sides by resistance. Resistance cancels out on one side, and we're left with power times resistance equals voltage squared. Square root both sides. Square root cancels out on one side, and we're left with square root of power times resistance equals voltage. This is yet another arrow in our quiver. This equation implies that given known power and known resistance, we can solve for an unknown voltage. You'll note this arrow is particularly sharp because it necessitates the user first multiply power and resistance and then take the square root of the product. By placing power times resistance in parentheses, it makes it painfully obvious that the product needs to happen before the square root operation. Do not poke yourself in the eye with this arrow by neglecting the order of operations. You now have 8 arrows in your quiver. As an exercise to the viewer, I invite you to solve for the following additional algebraic permutations. Given the original power formula, where power equals voltage times current, solve for the following. Given known power and known current, solve for voltage. Given known power and known voltage, solve for current. Additionally, use the permutation power equals current squared times resistance to solve for the following. Given known power and known resistance, solve for current. And finally, given known power and known current, solve for resistance. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Given power equals voltage times current, and given known power and known current, we should be able to algebraically manipulate this entry to solve for voltage. Divide both sides by current. Current cancels out on one side, and we're left with voltage equals power divided by current. This equation implies that given known power and known current, we can solve for an unknown voltage. Similarly, given power equals voltage times current, and given known power and known voltage, we should be able to algebraically manipulate this entry to solve for current. Divide both sides by voltage. Voltage cancels out on one side, and we're left with current equals power divided by voltage. This equation implies that given known power and known voltage, we can solve for an unknown current. Add these 2 arrows to your quiver for a current total of 10. Given power equals current squared times resistance, and given known power and known resistance, we should be able to algebraically manipulate this entry to solve for current. Divide both sides by resistance. Resistance cancels out on one side, we're left with power over resistance equals current squared. Square root both sides. Square root cancels out on one side, and we're left with the square root of power over resistance equals current. This equation implies that given known power and known resistance, we can solve for an unknown current. As previously, you'll note this arrow is particularly sharp because it necessitates the user first divide power by resistance and then take the square root of the quotient. By placing power over resistance in parentheses and extending the square root all the way to the bottom of power over resistance, and makes it painfully obvious the division operation needs to happen before the square root operation. Again, don't poke yourself in the eye with this arrow by neglecting the order of operations. Finally, given power equals current squared times resistance, and given known power and known current, we should be able to algebraically manipulate this entry to solve for resistance. Divide both sides by current squared. Current squared cancels out on one side, and we're left with power over current squared equals resistance. This equation implies that given known power and known current, we can solve for an unknown resistance. Ohm's law, when unified with a power equation, is incredibly versatile and can be used to double-check your work. In this spirit, I present to you what I like to think of as the grand unified theory of voltage, current, resistance, and power, sometimes collectively known as Watt's laws. This visual aid is a highly recommended addition to your cheat sheet. You'll note, given the numerous methods available, there exist multiple routes to a single solution. If one path is blocked, try another. I am encouraging you to find the method that works best for you. Develop your own style of problem solving and troubleshooting. Get good at it, get efficient, and don't make mistakes. If I present to you a method you totally suck at, practice it more or just plain don't use it. Use a method you're good at. Use methods you like using. My only demand is that you get correct results in the quickest manner possible. Let's put your understanding of these permutations to the test. I've given you 6 new arrows, and here's 6 new targets. Go fetch. Given the known values for each scenario, see if you can solve for the third unknown value using the most efficient and direct means possible. While you're there, see if you can use another algebraic permutation to check your work. Ideally, both calculations should yield the same result. Express all answers in proper engineering format to the 10th place. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Our first problem features an element consuming 600 watts of power and experiencing a 120 volt differential across it, where we're being asked to solve for the current through it. Current is equal to power divided by voltage. 600 watts divided by 120 volts yields 5 amps of current. A supporting calculation verifies this result. 120 volts times 5 amps does indeed yield 600 watts of power. Our next problem features a resistor with a color code of blue, gray, brown, gold, known to be dissipating 1.2 watts of power. We're being asked to solve for the voltage across it. A color code of blue, gray, brown means 68 with 1 0 after it, or 680 ohms. Voltage is equal to the square root of power times resistance. The square root of 1.2 times 680 demonstrates this resistor should be experiencing a 28.6 volt drop. The supporting calculation verifies this result. 28 volts squared divided by 680 ohms does indeed yield 1.2 watts of power. Our next problem features an unknown resistor known to be dissipating 6.4 watts of power and experiencing 80 milliamperes of current through it. We're being asked to solve for the unknown resistance. Resistance equals power divided by current squared. 6.4 watts divided by 80 milliamperes squared demonstrates that this is a 1 kilo ohm resistor. The supporting calculation verifies this result. 80 milliamperes squared times 1 kilo ohm does indeed yield 6.4 watts of power. Our next problem features an unknown resistor known to be dissipating 1.8 kilowatts of power and experiencing a 240 volt drop across it. We're being asked to solve for the unknown resistance. Resistance is equal to voltage squared divided by power. 240 volts squared divided by 1.8 kilowatts demonstrates that this is a 32 ohm resistor. The supporting calculation verifies this result. 240 volts squared divided by 32 ohms does indeed yield 1.8 kilowatts of power. Our next problem features a 50 ohm resistor known to be dissipating 700 watts of power, and we're being asked to solve for the current through it. Current is equal to the square root of power divided by resistance. The square root of 700 watts divided by 50 ohms demonstrates the resistor should be experiencing 3.7 amps of current. The supporting calculation verifies this result. Power is equal to current squared times resistance. 3.7 amps squared times 50 ohms does indeed yield 700 watts of power. Finally, our last problem features an unknown resistor known to be dissipating 270 milliwatts of power, experiencing 15 milliamperes of current through it. We're being asked to solve for the voltage drop across it. Voltage equals power over current. 270 milliwatts, or 15 milliamperes, demonstrates this resistor should be experiencing an 18 volt drop. A supporting calculation verifies this result. 18 volts times 15 milliamperes does indeed yield 270 milliwatts of power. Alright, hopefully that last set of example problems went well for you. If not, by all means rewind that last section and correct any mistakes you may have made. Again, it's often not the electrical concepts students struggle with, but rather the algebra and numerical literacy that hinders forward progress. As a general study skill advice, figure out what your problem is before you go see a tutor. No sense in practicing something you already know. Get to the root of the problem quickly and move on. Is it math? Is it numbers? Is it electrical concepts? Seek help on that topic and that topic alone before you move on. Let us now attempt to unify our previous discussions of energy and power and efficiency with our newfound appreciation of electrical power. Let's first review power and energy. As you are no doubt aware, power is energy over time. Algebraic permutations of this three-variable relationship also suggest that energy is power times time, and time is energy over power. Officially, energy is expressed in units of joules, although in practice, the unit of kilowatt hours is a more practical unit of energy, where 1 kilowatt hour is equivalent to 3.6 megajoules. If you've been following this lecture series in its intended order, you should already have some level of familiarity with energy and power. As such, let's roll right into an illustrated example. Consider a device that operates on 80 volts DC and draws 4 amperes of current. Let's say this device runs for 12 hours a day. How much energy in units of kilowatt hours does it consume every day? This is a two-stage problem. First, we need to determine the power rating of the device. Then, given this power rating, we need to determine the energy consumed after 12 hours of use. Power is voltage times current. 80 volts times 4 amps yields 320 watts of power. Energy is power times time. 320 watts times 12 hours yields 3,840 watt hours, or more appropriately, roughly 3.8 kilowatt hours. Too easy. Let's put your understanding of more sophisticated energy and power calculations to the test with a set of example problems. Given known values for each scenario, seek and solve for the desired properties using the most efficient and direct means possible. Express all answers in proper engineering format to the tenths place. Express energy in units of kilowatt hours. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Our first problem features a device that operates off a 120 volt DC, known to consume 5 kilowatt hours of energy after 8 hours of use, and we're being asked to solve for the power rating of the device and the anticipated amount of current draw. Power is energy over time. 5 kilowatt hours over 8 hours yields a power rating of 625 watts. Current is equal to power divided by voltage. 625 watts divided by 120 volts yields an anticipated current draw of roughly 5.2 amps. Our next problem features a device modeled as a 120 ohm resistor intended to operate using 60 volts DC, and we're being asked to solve for the power rating of the device and determine how much energy the device uses over a span of 16 hours in units of kilowatt hours. Power is equal to voltage squared divided by resistance. 60 volts squared divided by 120 ohms yields a power rating of 30 watts. Energy is power times time. 30 watts times 16 hours demonstrates the device consumes 480 watt hours, or more appropriately, roughly 0.5 kilowatt hours of energy. Finally, our last problem features a device that needs to accomplish a task that necessitates the expenditure of 1.2 kilowatt hours of energy, and it needs to happen over a 30-minute time span. In doing so, the device is anticipated to draw 8 amps of current. We're being asked to solve for the power rating of the device and the supply voltage necessary to operate the device. Power is energy over time. 1.2 kilowatt hours over 30 minutes, or 0.5 hours, yields a power rating of 2.4 kilowatts. Voltage is equal to power divided by current. 2.4 kilowatts divided by 8 amps demonstrates the device necessitates 300 volts to operate. Let us now review efficiency and its relationship to electrical power. As you are no doubt aware, efficiency is the ratio of usable power output over input and is typically expressed as a percentage. Previously, I asserted that power input to a system is always equal to power output. You might therefore be under the mistaken assumption that all systems are 100% efficient. This is undoubtedly untrue. However, it is true that all input inevitably goes somewhere, useful or otherwise. The truth can be found in the qualifier useful output. Allow me to demonstrate by way of a series of illustrated examples. Consider a 100 watt incandescent bulb and a 25 watt LED bulb, both designed to operate using 120 volts. Let's say both bulbs yield an equivalent amount of useful output in the form of 5 watts of radiant power. The efficiency of the 100 watt incandescent bulb is 5 watts of usable output over 100 watts input, which yields an efficiency rating of 5%. This is super crappy. Similarly, the efficiency of the 25 watt LED bulb is 5 watts usable output over 25 watts input, which yields an efficiency rating of 20%. This is still pretty crappy, but not nearly as crappy as the incandescent bulb. Let's say we use these bulbs for 4 hours a day, 365 days a year. This amounts to an annual usage of 1,460 hours. Energy is power times time. Over the course of a year, the 100 watt incandescent bulb consumes 146,000 watt hours, or more appropriately, 146 kilowatt hours of energy. Over the course of the same year, the 25 watt LED bulb consumes 36,500 watt hours, or more appropriately, 36.5 kilowatt hours of energy. If a user was charged, let's say 12 cents per kilowatt hour, operating the 100 watt incandescent bulb for 4 hours a day for a year would cost $17.52, whereas operating the 25 watt LED bulb for 4 hours a day for a year would cost only $4.38. The greater than $13 differential more than justifying the cost to upgrade to the more efficient 25 watt LED bulb. As if this was not enough, consider the current drawn by these different bulbs while in operation. Current is power divided by voltage. 100 watts divided by 120 volts demonstrates the 100 watt incandescent bulb draws roughly 833.3 milliamperes of current. Similarly, current is equal to power divided by voltage. 25 watts over 120 volts demonstrates the 25 watt LED bulb draws only roughly 208.3 milliamperes of current. As this example is intended to illustrate, this really highlights the clear superiority of the more modern efficient LED bulb over the hopelessly inefficient incandescent bulb. Not only does the LED bulb use less energy over time, thereby costing the operator less, it also draws less current. This may not seem dramatic. However, consider the design and construction of the electrical infrastructure meant to support a large number of facilities, all drawing smaller amounts of current. Given a reduction in current requirement, the size of the wiring, thus the weight and expense of the larger transmission system, can also be smaller. Here's another illustrated example of efficiency intended to differentiate between usable output and input. In a perfect world, batteries are ideal voltage sources with no internal resistance. In the real world, small imperfections negatively affect performance, and some output can be considered loss. Consider a real-world 12-volt battery, modeled as a 12-volt source in series with a small internal resistance of, let's say, 2 ohms, intended to supply an electrical load modeled as a variable resistor currently set at 60 ohms. You know, the gray box surrounding the battery and internal resistance is meant to imply that the internal resistance is part of the battery and cannot be isolated from it. Let's say any and all power consumed by the 60 ohm electrical load is considered directed towards useful output, and any power consumed by the internal resistance of the battery is considered a loss. The source needs to supply power to both elements. It can be said that power supplied by the source, i.e. power input, is equal to power consumed by the internal resistance plus the power consumed by the electrical load. Power in would equal power out. However, only one of the power outputs is considered useful, whereas the other considered a loss. This problem necessitates an understanding of series circuit properties, a topic we'll examine at length in later lectures. So for the purpose of today's lecture, I'll do the larger series analysis for you. That way you can concentrate on the 3 individual elements constituting the system: the source, the internal resistance, and the electrical load. Follow along as best as you can. The 12-volt source sees the series combination of the 2 ohm internal resistance and the 60 ohm electrical load for a total resistance of 62 ohms. Current is equal to voltage divided by resistance. Ohm's law demonstrates the source would provide roughly 193.5 milliamperes of current. Power is equal to voltage times current. The power input to this system is 12 volts times 193.5 milliamperes, or roughly 2.3 watts. 193.5 milliamperes of current travels through both the internal resistance and the electrical load. It can be said source current equals current through the internal resistance, which equals current through the electrical load, which all equals 193.5 milliamperes of current. Given the direction of conventional current travel, we should expect a voltage drop across the internal resistance, positive to negative, bottom to top, and a voltage drop across the electrical load, positive to negative, top to bottom. Let's determine the voltage drop and the power dissipated by the internal resistance first. Voltage equals current times resistance. An application of Ohm's law demonstrates the internal resistance experiences a small voltage drop of roughly 387.1 millivolts. Power is equal to voltage times current. The power consumed by the internal resistance is 387.1 millivolts times 193.5 milliamperes, or roughly 74.9 milliwatts. This small amount of power would be considered a loss to this system. Let's now determine the voltage drop across and the power consumed by the electrical load. Voltage is equal to current times resistance. An application of Ohm's law demonstrates the electrical load experiences a roughly 11.6 volt drop. Power is equal to voltage times current. The power consumed by the electrical load is 11.6 volts times 193.5 milliamperes, or roughly 2.2 watts. This would be considered useful power output. If we examine the efficiency of the complete system, of the roughly 2.3 watt input into the system, roughly 2.2 watts is directed towards usable power output, and only 74.9 milliwatts is considered a loss. This results in an efficiency of roughly 96.8%. Not bad. You note at the present operating condition, the electrical load only experiences roughly 11.6 volts of the available 12 volts due to the small drop across the internal resistance. This is what is known as the working voltage of a battery, which is in contrast to its nominal or nameplate rating of 12 volts. Given any power consumed by the internal resistance is considered a loss, we would expect the battery to exhibit some small degree of temperature rise, accounting for this inefficiency. Keep in mind these figures are snapshots of the system in its present configuration, and different operating conditions may yield different results. For example, consider the same battery modeled as a 12-volt source in series with a small internal resistance of 2 ohms. Only this time, the electrical load is a smaller resistance of 20 ohms. Let's examine this system in this present configuration and use our previous analysis as a basis of comparison. As previously, since we've yet to discuss series circuit properties, I'll do the larger series circuit analysis for you. That way you can concentrate on the power analysis of the 3 individual loads constituting the system: the source, the internal resistance, and the electrical load. Again, follow along as best as you can. The 12-volt source sees the series combination of the 2 ohm internal resistance and the 20 ohm electrical load for a total resistance of 22 ohms. Total resistance went down. Current is equal to voltage divided by resistance. Ohm's law demonstrates the source would provide roughly 545.5 milliamperes of current. Given total resistance went down, it is entirely understandable current went up. Power is equal to voltage times current. The power input to the system is 12 volts times 545.5 milliamperes, or roughly 6.5 watts. Given current went up, it is understandable that input power also went up. 545.5 milliamperes of current travels through both the internal resistance and the electrical load. As previously, it can be said source current equals current through the internal resistance, which equals the current through the electrical load, which equals 545.5 milliamperes. Given the direction of conventional current travel, we should expect a voltage drop across the internal resistance, positive to negative, bottom to top, and a voltage drop across the electrical load, positive to negative, top to bottom. Let's determine the voltage drop across and the power dissipated by the internal resistance first. Voltage equals current times resistance. An application of Ohm's law demonstrates the internal resistance experiences a roughly 1.1 volt drop. Given current through the internal resistance went up, it is understandable the voltage drop across it also increased. Power is equal to voltage times current. The power consumed by the internal resistance is 1.1 volts times 545.5 milliamperes, or roughly 595 milliwatts. This is considered a loss to this system. Given both current through and the voltage drop across the internal resistance went up, it is doubly understandable that power consumed by the internal resistance went up. The power consumed by the internal resistance might be directed towards a slightly higher degree of temperature rise, accounting for this inefficiency. Let's now determine the voltage drop across and the power consumed by the electrical load. Voltage equals current times resistance. An application of Ohm's law demonstrates the electrical load experiences a roughly 10.9 volt drop. You note at the present operating condition, the working voltage of the battery is dropped. This explains why the lights sometimes dim when you start a car driven by an internal combustion engine. The tremendous surge of current drawn by the starter motor temporarily results in a reduction of working voltage to all elements in the system. Power equals voltage times current. The power consumed by the electrical load is 10.9 volts times 545.5 milliamperes, or roughly 6 watts. This is to be considered usable power output. If we examine the efficiency of the complete system, of the roughly 6.5 watt input into the system, roughly 6 watts is directed towards usable power output, and roughly 595 milliwatts is directed towards losses. This results in efficiency of roughly 90.9%. Still not bad. However, you'll note at the present operating condition, it is less efficient than it was previously. This is to imply that properties like efficiency and working voltage are not static figures, but are rather dependent upon operating conditions. At the present operating condition, the battery is delivering more power to the electrical load. However, a larger portion of this input is being misdirected towards losses than previously, thus the lower efficiency rating. We'll have ample opportunities to examine batteries in more detail in later lectures. For now, you should simply appreciate that power can be calculated for individual elements, and for a larger system, all power input is inevitably directed towards some output, useful or otherwise. Additionally, you should be able to calculate efficiency and energy figures and understand how these properties relate to electrical power. Let's now examine electrical power transmission. In a perfect world, a source would deliver all power to an intended destination with no losses along the way. In the real world, the means of transmission itself extracts a degree of losses. In an effort to minimize losses in the lines, electrical power is ordinarily transmitted from a source to a destination using high voltage rather than high current. Ordinarily, this is done with AC electricity, a type of electricity that cyclically varies polarity and magnitude rather than DC. AC is its own weird beast, which we'll examine in greater detail in later lectures, but for the sake of this introductory discussion, let's just pretend they're equivalent. Consider a generator out in the sticks, operating at 700 volts DC, trying to transmit 2 megawatts of power to some distant city located in the shoe-wearing regions of the country using a 300-mile-long transmission line modeled as a resistor with 0.15 or 150 milliohms of resistance. This might not seem like much resistance, and you may instinctively presume that the line losses will be minimal. However, this is far from the truth. I must remind you that power is equal to current squared times resistance. Even a small resistance carrying large amounts of current will dissipate tremendous amounts of power. In this case, any power dissipated by the transmission line would be considered a loss. This generator is producing 2 megawatts, 2,000 kilowatts, or 2 million watts. This would be considered the input to the system. If current is equal to power over voltage, if you tried to transmit all 2 megawatts of power using 700 volts, this would necessitate the transmission line carry 2 megawatts over 700 volts, or 2,857.1 amps, or roughly 2.9 kiloamps of current. This is an astronomically large amount of current. An application of the power equation, where power equals current squared times resistance, demonstrates the line will dissipate 2.9 kiloamps squared times 0.15 ohms, or 1,224,489.8 watts, or more appropriately, roughly 1.2 megawatts of power, more than half the power being sent by the 2 megawatt generator, leaving only 775.5 kilowatts for the distant city to put to good use. Long story short, the generator makes 2 megawatts, or 2,000 kilowatts, but the city only gets 775.5 kilowatts. This scenario results in an extremely poor efficiency rating of only 38.8%. A majority of the generator's power input is expended not in powering the distant city, but rather in turning the transmission line into a 300-mile-long toaster. This cannot and will not work. High current results in massive amounts of line losses, and substantially less input is directed towards useful output. It is largely for this reason electrical power is generated and transmitted using AC rather than DC. AC electricity, in contrast to DC, allows for the use of a device known as a transformer that steps up voltage at the same time stepping down current, and vice versa. We'll examine AC power and transformers in later lectures. Consider the same 2 megawatt generator transmitting power to the distant city along the same transmission line modeled as a 150 milliohm resistor, not at 700 volts, but rather at 35 kilovolts, or 35,000 volts, 50 times greater than previously. How will this marked increase in transmission voltage affect the efficiency of this system? Given current is equal to power over voltage, if all 2 megawatts of power were transmitted using 35 kilovolts, this would necessitate the transmission line carry 2 megawatts over 35 kV, or 57.1 amps of current, i.e. 50 times less than previously. By stepping up voltage, we can transmit the same amount of power using substantially less current. Let's examine losses in the transmission line. An application of the power equation, where power is equal to current squared times resistance, demonstrates the line will dissipate 57.1 amps squared times 150 milliohms, or roughly 489.8 watts, of the available 2 million watts for the distant city to put to use. Long story short, the generator makes 2 megawatts or 2,000 kilowatts or 2 million watts, and the city gets 1,999,510.2 watts. For all intents and purposes, all 2 megawatts. This scenario results in a much better efficiency rating of 99.98%. One more short example before we bring this lecture to a close, this one intended to illustrate how extremes of voltage and current affect power calculations. Consider a photovoltaic panel, or a PV panel. PV panels are characterized by something known as an IV curve, where voltage is on the horizontal axis and current is on the vertical axis. As a simplification, increasing levels of light intensity increase current output of a solar panel. At an intensity of 200 watts per meter squared, the IV curve might look something like this. At an intensity of 400 watts per meter squared, the IV curve might look something like this. Light of increasing in intensity yields a similar pattern up to something known as standard temperature and conditions, or STC, whereby the panel is illuminated by light of a standard intensity of 1,000 watts per meter squared. This is the performance standard used by most panel manufacturers to rate their product. When you buy a 300 watt solar panel, it means it produces 300 watts when it is exposed to light of 1,000 watts per meter squared intensity. This is what is known as the maximum power point, meaning it is the most ideal scenario where power is at a maximum. As you're no doubt aware, power is the product of voltage and current. Maximum power does not necessarily mean maximum voltage nor maximum current, but rather maximum power is an occasion in which the product of voltage and current is at a maximum. PV panels often include a datasheet which specify the voltage and current at the maximum power point. For example, consider a panel that produces 300 watts at STC with the following characteristics. At the maximum power point, voltage is known to be 32.48 volts, and current is known to be 9.24 amps. Power is equal to voltage times current. 32.48 volts times 9.24 amps yields roughly 300.1 watts of power. What do we make of the other data points on the IV curve where the solar panel is operating at less than maximum power conditions? For example, consider the open circuit voltage, where voltage is respectively high at 40.45 volts. This would be the far right side of the IV curve at this given intensity. As the title open circuit implies, the panel does not have a conductive path and no current flows. Power is equal to voltage times current. 40.45 volts times 0 amps yields 0 watts of power. Additionally, consider the short circuit current, where current is respectively high at 9.91 amps. This would be the far left side of the IV curve. As the title short circuit implies, the panel does have a conductive path, however, no voltage exists. Power is equal to voltage times current. 0 volts times 9.91 amps yields 0 watts of power. You'll note both extreme occasions, open circuit conditions with maximum voltage and 0 current, and short circuit conditions with maximum current and 0 voltage, yield output not just less than maximum power, but 0 power. If we multiply voltage and current for all points on the IV curve and overlay a plot of power in the same graph, we'd observe something like this. The power curve goes from 0, climbs to some maximum, peaks out, and begins to fall, where the maximum power point is the ideal scenario in which power, the product of voltage and current, reaches a maximum, in this case, roughly 300 watts. Alright, one last thing, I promise, before we close up shop. As I mentioned earlier, the measurement of power necessitates a technician choose between 3 available options. First, a technician could take a voltage reading using a voltmeter, then take a current reading using an ammeter, then multiply the voltage and current reading together to obtain a power figure in units of watts. Second, given a known resistance, a technician could take a single voltage reading, then square voltage and divide it by resistance to obtain a power figure in units of watts. Finally, given a known resistance, a technician could take a single current reading, then square current, and multiply by resistance to obtain a power figure in units of watts. A fourth method exists using a device known as a wattmeter. A wattmeter is a special purpose instrument designed for single-step measurements of power where no calculation is necessary. One can visualize a wattmeter as a box or a bridge with 2 meters inside. One measures current and the other measures voltage. Internal circuitry performs a multiplication operation and a result in units of watts is displayed as an output. Typically, a DC wattmeter is installed as a 2-input, 2-output bridge between a source and a load. 2 input terminals, ordinarily labeled line, are connected to the source terminals. and two output terminals, ordinarily labeled load, are connected to the load. Arranged in such a fashion, the ammeter portion of the wattmeter measures current from the source through the load, and the voltmeter portion measures voltage across the load. Sometimes you might see 3-terminal wattmeters, where the bottom terminal serves as a common terminal to the input and output pair. Importantly, consider the placement of the meters internal to the wattmeter. Voltage is measured across something, whereas current is measured through something. The wattmeter just serves as a single bridge between our input and output if our only measurement concern is wattage. That's all I've got for you today regarding power. This single topic tied together a number of previously unrelated topics, and it is entirely understandable and encouraged that you revisit this topic if necessary. Moving forward, realized progress will be predicated upon your understanding of previously covered material. In this basic lecture, you've already got an appreciation of how power calculations are directly related to high-level topics like power transmission and photovoltaic systems, and this level of interconnectedness will only become more important as we progress through this series. In conclusion, this lecture took a close look at the different permutations of power calculations for DC power, sometimes collectively known as Watt's laws. We additionally reviewed power and energy and efficiency calculations and introduced a common device used to measure power, the wattmeter. Additionally, we had a preliminary discussion of the importance of power calculations related to the transmission of power and alternative energy sources. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.